Life is about learning, and what we want to get out of life and what we expect to learn is often not what we actually get. Our expectation, what we set out to achieve or learn, doesn't necessarily always overlap with what we actually end up learning. And when working on this talk, that was actually the first realization I had. I learned something I did not expect to understand at all. Specifically, that if you add the word recreational to the front of anything, it instantly becomes more fun. Just look at this list. All of those activities are way more fun if you add the word recreational to them. And the reason I came up with this revelation or this unexpected learning is because I started researching John Horton Conway. He's a famous mathematician, has furthered the field of mathematics in lots of different ways. Cellular automata is one that is well known. But one of the other aspects that I learned about him is that he's considered one of our preeminent recreational mathematicians. And if you hear the term recreational mathematics, you probably are in two different camps. One camp says it's math. Everything about it is fun, therefore all math is recreational mathematics. But you're in the other camp that says it's math, nothing about that can possibly be fun. But the concept of recreational mathematics is built on the idea of let's do something for entertainment, maybe specifically as opposed to specifically for research. And one of the contributions he had was he invented what's known as Conway's game of life. He was thinking about a problem and trying to come up with a way to, use it in a fun or creative way. And this was published in October of 1970 in the Scientific American in a column called Mathematical Games. And he described his game of life, set it out as a challenge for people to think about and play around with. But really what it was a simplified version of universal constructors from John von Neumann in the 1940s. Von Neumann was trying to build self-replicating machines and had, various success of doing it in the physical world, at circuits, etc. But with mathematical proofs, he was able to do it on a grid. But it was very complex. Each cell could be in a series of 0 to 29 different states for it to actually be physically possible. So Conway, when seeing this problem presented, thought, can we do something simpler? Because trying to reason about 29 different states of every single cell across this grid could be a little bit complicated. And so he had some goals. I want to still be able to support the concept of universal constructors, but I want to vastly simplify the rules. His game actually is set up to only have two states. You're either alive or you're dead, not 29 different ones. But he also wanted the ability to kind of be surprised by the outcome and be surprised by the results and have these unpredictable outcomes built off this small little pattern. So what is the premise of the game? Specifically, we set up the world that's completely randomly generated. Certain cells will be alive, certain cells will be dead. It'll be infinite, spanning in many directions. Typically, this is thought about in a two-dimensional world, but we actually have visualizations that are in a three-dimensional world. Just think about the giant screen that we have at the Innovations Campus. It has some super awesome visualizations of Conway's game of life flowing on it. And it actually does it in 3D. The other is kind of atomic transitions. When we have the state of the world and we know it, we calculate what the new world should look like and then immediately transition to that. No longer are those intermediate transitions affecting other situations. We literally pick up the world, recalculate it, and put it back down. And in addition to this simplified set of rules, or simplified problem constraint, he also simplified it down to having 4 basic rules. The first rule is that any live cell with fewer than 2 live neighbors dies as if caused by underpopulation. So we have 2 live cells on the board, we count up their neighbors, and we see that the world ends. Any live cell with 2 or 3 live neighbors lives on to the next generation. This is the second rule. So once again, we look at that cell, we count up all the neighbors, we figure out that nothing dies, the world just continues to exist. The third rule is that any live cell with more than 3 live neighbors dies as if by overpopulation. So we calculate everything up, we see that there's 2 with 4 neighbors, and those pass away. And then the fourth rule is that any dead cell with exactly 3 live neighbors becomes a live cell as if by reproduction. This rule kind of adds a new twist to the problem. No longer are we just counting up the neighbors of the live cells, we actually have to count up the neighbors of all the dead cells as well. So we fill this out, and we see that there's 2 cells with exactly 3 neighbors that are dead, and they would become alive. And the purpose of this game is to keep applying all 4 rules at the same time. So we start with what I showed was that rule number 2, static situation, nothing changes. But we apply all of the rules. What we see is that 2 cells come alive based off of reproduction. Then 2 cells will die due to overpopulation. And then the rest of the world ends due to underpopulation. So it is the end of the world as we know it, and we're fine. What's interesting is this kind of thought of recreational mathematics. It was written in an article, and it had various challenges. Can you devise a situation that follows these rules and iterates within a certain number of iterations, or will continue to grow and expand infinitely? And there were $50 prizes, and most people started to solve these problems using chalk or pen and paper or using the Go board game. And these are kind of some of the patterns that they devised and came up with. Some of them are really cool. Some of them just oscillate between 2 different states. Some of them take 15 different states to iterate before they start to repeat. And some of them, like the glider or the lightweight spaceship on the far side, go and continue to traverse across the entire board. And so you kind of think about this kind of cool idea of an infinitely large world where all of these different states are kind of happening at various points and various corners and interacting with each other because they'll collide potentially. And so while it was a cool idea in the 1970s, it hasn't really died there. I first was kind of introduced to this in the 2011-2012 era because as programmers, we like to continue to challenge ourselves or show off our prowess. We start to see things like, can you implement this entire game in a single tweet? And then not to be outdone in the language of Clojure, it's not specific to that one, someone did it in Ruby, in F#. In fact, I found instances where someone actually solved the game of life in 140 bytes of JavaScript. That was the challenge they set out for themselves. Once again, none of this is really practical, it's all kind of recreational and fun. The examples don't really stop there. There's more than a few Twitter bots purely dedicated to generating visualizations of the game of life. XKCD actually references the game of life in its comic. One of the interesting features of the game of life is it's actually Turing complete, meaning you can start to implement logic using that. Somebody actually decided to build the game of life into a Google Sheet. The best reason is you can see at the beginning of their blog post. Why did I do this? Because. You can even get way more complicated. There's a challenge. Can you implement a digital clock with the game of life? And there's the problem statement. You can actually see that this is a follow-up to being able to build the game of Tetris in the game of life. But you see a GIF of what that person actually was able to produce. The other way I encountered Conway's game of life was I was fortunate enough to attend a code retreat hosted here at Cerner. It's a day-long experience where you spend 6 to 8 different sessions pair programming with someone else. And each session, though, you're trying to solve Conway's game of life. But instead of just, the goal is actually not to complete the game, but to maybe try out and learn something along the way. Can I implement it not using lists or loops or a functional parameter? Maybe I want to try learning a new language. I'm inexperienced with the language of Go. Can I do that by pair programming with somebody and get it implemented? Or there's actually variations on the game of life, like the immigration one, where you actually care about what your ancestors are, being a certain color or a certain number. It's a great teaching tool to think about as far as you trying to tackle new methodologies. So then I kind of started to try and expand on this. I want to take a problem that people solved on chalkboards and with pens and paper, or can run on a single machine in Bash or in whatever language. Can I do something you don't need to do with it that's really probably pretty dumb? And would I be wasting everyone's time if I took the time to do that? And I felt bad, because it would be dumb. But then I felt I could justify it, because it's actually going to be recreational. Specifically, the goal was, can I use the game of life to help in learning distributed systems? Probably most of us are frustrated with a situation where when you are reading the Get In Started or the Quick Start with a new language or a programming paradigm, it looks something like this. They have those examples on the left side. Look, it's so easy. But then when you actually try to get to doing your real work, it's a giant leap. Could I use the game of life as some kind of intermediate step or a personal problem to kind of grow and learn along the way. So, before I started trying to learn a new distributed system or anything like that, I probably need to at least establish a basic algorithm for how to solve this. There's tons of ways to solve this. Everyone can set their own constraints, challenge themselves in different ways, but this is how I went about it. Specifically, my goal was to be efficient in what I had to actually track and be able to support that infinite board. So I couldn't kind of constrain it to an array or an array of arrays or anything like that. So I'm only going to track those live cells, because really what I need to know is this cell alive or dead, and how many neighbors it has. And for dead cells, I only need to care about those dead cells that are right next to live cells. So I could derive them from only tracking the live cells. So I start with this as my initial state of the world. I then go and take the very first one, and I want to blow out markers for all of its neighbors, so I can start calculating the neighbors for it. So I'll emit false for all of its neighbors and emit true for itself, so I'm keeping track of whether, what the neighbor counts are, as well as its current state. And I do this for each value. And so I end up with this giant board that looks like this. So now what I want to do is I want to kind of evaluate every single cell and know whether it's alive or dead and what its neighbor count is. So I'm going to pick an arbitrary one. Here I see that I have one cell that is alive. That means that that cell was alive in the previous generation, and that represents itself. And I have two neighbors that are false, which means those are two neighbors that are dead. So I am alive, and I have two neighbors that are currently alive. Therefore, this should maintain a state of staying alive. If I look at a different cell, here I see three instances where nothing is true, so nothing is alive. So that means that cell is currently dead, but I have three neighbors. Therefore, this cell should come alive. And then again, if I look at this cell, it's currently alive because there's an instance of true. It only has one neighbor that's false, so therefore I only have one live neighbor, and I should technically die. And I'm going to keep doing this for all the coordinates until I actually can get the final state, where I see everything in red should die, and everything in blue is alive. So I don't care about any of the dead ones. Let me filter those values out, and let me kind of combine this back down into a single value. And then what it should see is that implemented the blinker pattern, or the blinker situation of the game of life. And if you're a functional programmer, it's very easy to think about, because it's basically a flat map, then a reduce, then a map, and then a filter, kind of chaining all of those functions together. So I have an algorithm, and now I want to try and tackle the distributed systems. In distributed systems, you kind of have two different worlds, the batch world and the streaming world, or the bounded and the unbounded world. Which one should I pick? And I'm going to tackle both of them, but let me maybe start with the easiest one to see if this problem actually translates very well. Specifically, one part of the problem that translates really well is this concept of atomic transitions. Bounded or batch processing is all about taking a large, vast amount of data, picking it up, processing the new state, and putting it back down. So let's start there. The analogies work very well, and the problem is easily solved, in theory. So we can also then pick one of the many distributed systems bounded batch processing. Let's stick with MapReduce. Specifically, the code examples I'll show were all written in Apache Crunch, purely for the sake of ease of developing and things like that, but the workforce behind it is a simple MapReduce job. So I need to start with reading in the game board. Here you see that at the very bottom of the text, I read in that P collection of all those cells. That should only represent those live cells. Then I need to generate the neighbors keyed by the coordinates. So here I take that world, I apply a function to it, I get back another table that's kind of keyed by those coordinates of that self and all of its neighbors. From there, I need to aggregate them by key, which is done by a simple group by key. That will ensure that all my cells that have a certain coordinate are going to end up in the same location across thousands of machines. I'm going to apply the rules based off of all those values getting aggregated together. You see here I take the parallel do, I apply the rules to them, and I get kind of the next generation. But the current state is actually I have both the live and dead cells. I know that this cell should be dead and this cell should be this cell should be alive. So then I need to filter those out. and that's a simple filter added on to the end. And then this is the part where using bounded or batch systems doesn't maybe make the most sense. They're very good at picking up the data and landing it, but they're not as proficient at bounded, or excuse me, at iterative functions. And so I kind of have to write my own driver program to say, all right, you've landed it, now pick it up and do it again, and then pick it up and do it again. But one of the things to think about is now that I've written this in MapReduce, I've maintained the state in the rules of the game so it actually works, but I get all of these benefits as well. In theory, I actually just have to extend the coordinates to be able to handle 3 dimensions instead of just 2. I'm scalable to however much data I actually want to pick up and process. It's very actually memory efficient in that I don't have to worry about that much data being aggregated together. The last 3 are actually very interesting. I have completeness. I know the accuracy of the world is correct, and I don't have to worry about any interjected or intermediate failure points. I have recovery points and known predictable failures if something was to actually go wrong. Since I can be atomically transitioning the world, I know if my job fails, I just go to the last state of the world and keep iterating. So it actually works really well, and this analogy kind of fits. So I wanted to see if this analogy continued to the next algorithm, or the next kind of batch processing. And so Apache Spark is a well-known processing engine. Its focus is more on in-memory as opposed to writing things out to disk or the rigid structure of MapReduce. But it actually kind of has a very common or similar pattern. I can actually use the same algorithm to solve the problem in the exact same way. Or more specifically, I can use almost the same algorithm. Because the minute you start researching how to write this in Spark Batch, you're going to find yourself hitting an anti-pattern. Specifically, you should never use group by key. What they actually suggest is the reduce by key, which means you kind of do some combination of your logic where the data lies, only transfer what's actually needed, and then recombine at the absolute end. So this part of my processing has to get rewritten. Specifically, to be able to do reduce by key, I have to change the algorithm to be commutative and associative, because I can't apply the rules with only part of the data and then reapply the rules again with only part of the data. I might decide a cell is dead or discard different things. So I actually need to change it to do this, where I generate the neighbors, still keyed by the coordinates, but also with counts associated with them. I then summarize the counts, which can be the commutative and associative part, and then only apply the rules at the very end. For the sake of brevity and because it doesn't really add much to the context, I'm not going to show you the code, but the algorithm actually ends up working as well. And the same optimization that is enforced or encouraged in the Spark batch actually should probably be applied back to the MapReduce example, just for the sake of pure efficiency. But this is a recreational idea, so it doesn't matter that much. So now that I've kind of tackled the bounded batch side, what about the unbounded side? And this is probably where I spent the most time thinking, like, does this even make sense to try to tackle? On one side, if we're trying to simulate life as we know it, trying to reason about or be able to encapsulate and describe the entire world right now at this given point seems impossible. People are moving around this conference center. Things are shifting at a subatomic level. Being able to accurately describe it, tell everyone to not move, and then pick it up, reprocess, and tell them where they're going to be next seems really unreasonable, not very good of a simulation. But to be able to handle that constant update or not being able to handle the world, can I actually use and solve this game without the guarantee of atomic transactions? Because I'm not guaranteed to know what the state of the world is, I'm not able to basically calculate the next state without also having to deal with new data coming in, possibly changing things in intermediate state, messing things up. And this problem presented itself, and I started trying to reason about something we all are challenged with in the big data distributed space. This kind of giant divide between bounded and unbounded. If I'm doing bounded processing, I use technology X, and this is how I write that code. If I'm dealing with unbounded, I'm using technology Y, and this is how I deal with that code. And then I have to make my life ridiculously complicated to try and merge the two back at the end. We kind of have this giant segmentation where they're separated. But I'm trying to actually merge them, or I'm trying to maybe solve them in the same way. And so one of the interesting things is over the last few years, the lines between them have slightly become blurred. They're not just two distinct worlds, there may be different perspectives on the exact same thing. So it's, yes, I'm thinking about it and interpreting it differently, but maybe it's the same object or the same thing happening behind the scenes. And this kind of merging of the two worlds has came about a few years ago, specifically when Google released its Cloud Dataflow API. It started to break down that wall. Prior to Cloud Dataflow, we had systems where this is your batch processing system, this is your streaming system. Google went through the same evolution. They've just been doing it in secret or private, and then now starting to expose it. But they kind of said, hey, if you think about the problem in a certain way, you could use the same API to solve in both situations. And that's kind of cool. And this idea has kind of been carried forward in a lot of other systems. All of these projects kind of present this idea of an interrelationship between batch processing and streaming, or the terminology they use is tables and streams. Apache Beam, which is just the kind of open source version of Google's Cloud Dataflow, has that same simple API. Apache Flink and Apache Spark both have APIs that are very similar. Spark has something called structured streaming, which is trying to represent the table and stream duality. And Apache Kafka, while known really well as a distributed commit log or a queuing type system, actually started to introduce processing libraries that are specifically highlighting the duality of streams and tables. In fact, some of those ideas came about from the original authors of Apache Kafka, Jay Krebs and Martin Kleppman, who presented this idea of everything being interrelated. So what if we define streams and tables? Specifically, we no longer think about the form of the data or how it's actually formatted, but tables are simply data at rest. And streams are data in motion. If we think about it that way, we actually see that during a normal MapReduce or batch processing, the data actually transitions between being a table at the very beginning to being a stream as it's going through the processing steps to then being a table at the very end. So already we're kind of mixing the two worlds together. But the concept is also further extended. Is there a way that we can take the stream, apply the function or what that stream represents, and be able to generate a table? And can we also kind of, using that table, generate a stream of what's actually happening? It does require a certain mental shift. No longer are we thinking about the data as simply what is the next state, but we think about the streams as actually being the log of changes that are going to happen. So, no longer is it here's the state, 0, 1's alive, 1, 1's alive, 2, 1's alive, but really these are inserts. These are the next state of it. It could be updates, or they could be deletes. Tables are basically caches of the changes so far. Here's a snapshot of what all the changes that have ever happened should be applied. So we go from that stream to then generate a table, maybe how we commonly think about it down below. And we do this generation of the table based off of triggers. Based off of these conditions, we will create this table. Now, the common triggers that are used about most of the processing libraries are the concept of windows, sliding, hopping, tumbling, you name it, or watermarks. Is the data at this point on time, or early, or late, or sessions, periods of inactivity, or punctuation? Usually these are built on some concept of time that's inherent to the data. When did the data occur? Processing time, when am I actually perceiving the data? Or ingestion time, when did it actually get pushed into the system? There's also, and these could be actually wall clocks or logical clocks, depending upon what makes sense. So, out of the litany of streaming systems that I probably could have chosen, I decided to try and implement this using Kafka Streams. Specifically, since the concept came from some of those authors, it's a newer library, it has some unique capabilities, let's try it out there. So Kafka Streams first has a different concept than a lot of processing systems. Most systems are in this model. I write a little bit of code, it sits on a driver process, I then submit it to a giant cluster that will do all the computations for me. Kafka Streams actually says, we don't want to worry about the giant cluster. We're going to take this processing library and embed it inside of your application to actually do that work. And it has some additional benefits like interactive querying, state caching and querying, etc. so that your application could actually read and write data out of Kafka Streams. But if you want to scale to more parallel processing, you end up spinning up more instances of your application. And all of these instances are mostly independent. When they require coordination, they actually write data back to the Kafka cluster itself. So when I need to group all data by a specific key, I write it back to Kafka in a guaranteed known location. This seems a little wonky, especially when you think about things in a MapReduce world where you try to avoid writing things to disk unless you absolutely have to. In this case, they're banking on the guarantees of Kafka cluster being really fast for reads and writes to handle that problem for us. Here's the architecture diagrams that you kind of get for free from Kafka Streams. It shows the concept of building topologies for your processing. On the left side, you actually see the architecture as far as how you can embed it in various components. So inside of a specific application, you have this processing topologies. What's interesting about the diagram is it shows that Kafka Streams also builds in resiliency through local state or potentially storing off to a database or RocksDB instance, et cetera. And that plays into effect when we get into failure scenarios. But specifically about Kafka Streams, it has two parts. It has a processor API that is very low level, kind of like, here's my processing, let me duct tape it to the next piece, let me duct tape it to the next piece. But it also has a stream DSL that's maybe more intuitive and natural to use, similar to what we've done with other languages or other distributed systems in trying to solve this problem. What's also interesting is in that DSL, it kind of builds in a first-class way of transforming and migrating from a stream back to a table. So that kind of relationship is hard-coded into the library. If I want to go from a stream to a group stream, I do a group by key. If I want to go from a group stream to a table, I want to aggregate and reduce it. And anytime I want to actually change it back into a stream, I just call a two-stream method. So the concept of having a table of all of the changes being applied and then transforming it back into the changes that are coming through the system is actually very easy to think about, or very easy to do depending on your processing needs. So here's the code that does this. And in this case, I'm kicking off. I'm reading the data out of a specific topic in Kafka. It's keyed by the coordinates in the cell. And it's also kind of stored in a cache called word store for me. I then want to do the flat map algorithm that we talked about. Then I generate all of the neighbors. And then here's where a little bit of code gets complicated. I do the group by key, so that actually behind the scenes, without me knowing it, or with me knowing it, but without me having to care, writes the data back out to Kafka in a certain way that it'll guarantee each system will get the right key and be able to apply the logic. It applies the function to kind of reduce and combine all my counts together. Here's where I'm actually telling it to do this in a rolling 10-second window. And lastly, I kind of will store this back out into reduce. So if I have any failures or anything like that, it'll be able to resume based off of this current table. From here, I take that reduced values, or that reduced collection table of values, and I start to apply the algorithm to it. And I build and I emit the new world. And then, of course, to make this a constant iterative thing, I take that data, write it back out to Kafka, which should, in theory, kick off the entire process one more time. So if I start with a world that looks like this, that's the table I've read out of Kafka in that initial table, I should end up with, it alternating from being a blinker, from being horizontal to vertical. But instead what I end up is this, and that's not quite right. My algorithm expects me to only be tracking the live cells. And that's part of the problem, is I wrote the algorithm building off of the old concepts to be thinking about the future state, and that's what I'm calculating, when what I really should be thinking about is the changes necessary to get me into that future state. So specifically what was happening behind the scenes is the output was interpreting as this is an insert, this is an update, this is another insert, this is an update, that's an update. I needed to actually track the concept of deletes. I should be removing things. I should be killing these cells off. And I do that, if you read the documentation, which I should have done earlier, you see that to simulate a delete, I actually need to return a null value. So what this does is, replaces those false, gives it kind of tombstone markers, tells that data that it should go away. So then when I run this, this is kind of the output I'll start to get. And I realize it's a wall of text, but you basically see that it's blinking from being horizontal to vertical, etc. And I've been successful. I just translated something that was written for kind of the bounded batch world into a streaming world. And for those who have great eyesight, they realize there's an asterisk. I made some mistakes. Or the way the system implemented things caused me to make mistakes. Specifically, one mistake that I've made was I built in the concept of a logical clock. There's a generation marker to help me know when I'm transitioning from one state to the other. Most of the new processing libraries, like Spark Structured Streaming or Kafka Streams, only work off of wall clocks. They expect their time to be relative to a wall clock to handle certain evaluation. So originally, that's a problem for me. The second is specific to Kafka Streams. While I expected the general idea to be like, at a certain time interval of 10 seconds, let me generate the table, Kafka Streams actually does windowing on a key-by-key basis, not off of the entire state. So what that means is each kind of cell is windowed individually and not as a giant holistic board. So that causes a problem. The other problem is that windows are semi-fictitious in Kafka Streams. They aren't really kind of, here's the data and I'm guaranteed to emit it at a certain time. What it instead does is kind of namespaces that key by a time. So any updates within that time of 10 seconds are all going to get the exact same key. They aren't going to hold on to it or retain it and wait for other data to come in. So what actually happens is the data goes through the reduce and then goes through the map immediately with only a partial amount of that data, and that map function is not associative or commutative, meaning I start to apply and break rules. So my example that followed the blinker pattern only actually works due to luck and how the data was actually written in, how it gets sent across the system, and actually get interpreted. The order that the events were received during that reduce is what made this magically work. So my example failed, which sucks, but while we're on the topic of failure, what else did I do to the system? I had all these guarantees in a MapReduce batch world, but I made life complicated for 3 of them specifically. I don't have recovery points. I don't know whether I did partial writes when I was transitioning between different states. I don't know if I'm evaluating or guaranteed to have all the data to kind of have this concept of completeness to know that my world is transitioning. And I don't have predictable failure either. Who knows what was happening at the time a system crashed? Some of these are not a problem. Some of these, when you read the documentation for the various streaming distributed systems, like recovery points, they have well-known established patterns. Specifically, Kafka Streams builds in caches local to the systems for you to recover from quickly. They also use Apache Kafka as the data store behind everything to be able to kind of resume and pick it up by a different process. So recovery points, not actually a big concern. The streaming systems usually handle this for you, and this is true of things like about Apache Spark Structured Streaming. But regarding completeness and predictable failure, I have a problem actually when I'm translating the problem itself. Specifically, what happens when data starts to arrive late? Maybe a write is failing or something's stalling out from a network connection so that in that 10 seconds I don't get all of the calculations or all of the correct state of the world. But I also have the problem of changes are non-idempotent, meaning an insert or a cell becoming alive has to happen at a certain generation. If it happens too late, it'll completely skew the way the board works. So how do I deal with these? And both Kafka Streams and Apache Structured Streaming talk about solving it with basically 2 methodologies. So let's start with the ideal state of the world. This is the glider example. As you see, it kind of starts in one corner and will slowly traverse across the world at various clock tick intervals. If I take the first stage, the output from it are basically deletes, inserts, and more deletes. But let's split this up. What if only half of those changes arrive at time t+1, and the other half don't arrive until time t+2? What am I going to do with this? So the first solution they talk about is apply the changes to that window of time and just go on with it. So what would that actually mean? The data arrives at time t+1. As you can see, there's a cell that should have been deleted is still alive. Other cells that should have come alive are not present. I reevaluate the rules, and I kind of see that, it's no longer that glider shape. And by the fourth period of time, I've actually, caused mass extinction across the entire world. Not a great example. The other solution is using something like watermarks. Now, watermarks are very complicated. There's a lot of guarantees in various systems, but kind of the guarantees of something like Kafka Streams is that if the data arrives too late, just discard it. Don't do anything with it whatsoever. So how does that change everything? So in this case, those upper values will never arrive or never get applied, and I see the world morph. And instead of it dying early or continuing on forever, it'll die at time t+5. So I end up with these 3 different realities based upon how I need to handle this data. The top one being the ideal way it should work, and the other ones being using the different methodologies for handling failure. None of them are great, but that's okay. This is for fun. What I really need to actually solve this is something that's talked about in the Streaming 101 papers from O'Reilly, is this idea of refinement. Now, this is a fun thought experiment, one I actually wasn't able to think through and implement, but what I really need to do is take that late arriving data, go back to the phase or window it should be applied, and recalculate the world from there. But then you can kind of think about data is always going to be late arriving, and you basically are going to come up with this giant multiverse of what the world is actually supposed to be. And so you kind of need to start bringing in other systems to probably maintain state and deal with it. Fun problem to think about, not one to actually easily solve and give in a presentation. So for this presentation, I actually generated 4 different examples. The MapReduce one, the Spark batch one, I implemented one with Kafka Streams, and I actually implemented one with Apache Spark structured streaming as well for everyone to look at. All the code is available there, way more well documented than what I've done here. But to be honest with you, there's bugs with both the structured streaming and the Kafka Stream ones, so pull requests are welcome. If you think of other situations or other libraries that you want to play with and experiment with and show the example, I'll take pull requests. But if we go back to the original question, can the game of life help in learning distributed systems? I think the answer is yes. Now, what it helps in learning is probably up for debate, because this is probably all the list of things I've learned trying to do this presentation. And this wasn't really what I set out to learn. I actually would love to say, hey, I've learned how to use these technologies. I can now apply that same methodology to solve all of our problems. Probably not, but I at least got some good insight to how this thing will handle and how it will work, and whether or not the concept of streams and tables actually makes sense. And I think it does in certain situations. You just have to think about how the data changes. And what I really wanted was to basically come away with some talking points or some specific things that everyone should learn and drive home. But I didn't necessarily. It's all for fun. I didn't actually have to. That's kind of my reasoning for why I don't have that. But I do have kind of 2 edicts for everyone. The first, try implementing the game of life in some way. Pick a way, whether it's a new language, building it in a JavaScript web UI, in a bash script, who knows what you want to do. Think of creative ways to implement it and do it, and try it. You'll probably learn something along the way. You maybe are going to get code you're going to easily throw away because it doesn't actually matter, but give it a shot. And the last challenge is to be recreational. Who knows what you're going to find out, what fun's going to be had, and whether or not someone's going to be talking about it 40-some years later after you published it in a magazine article. Here's a lot of the references I used to build up this talk. Lots of great intros to the various technologies we use, as well as some thoughts and methodologies. The one I actually highlight that's really interesting is this Google Doc about was published by the Apache Beam people regarding their views on stream processing and tables as well. So give it a read, and please leave some feedback. Thank you.